Alright everyone, welcome back. So, let's continue with this here. We'll start off with something again, a review of what happened before. What happened in earlier units here. So we have a triangle ABC like this here, and we're told that AB is equal to BC. Okay, no big deal. BE bisects angle ABC. Well, you know what an angle bisector does? It splits this angle on up here in half. We can kind of do something like this here. Well, can we draw about the segments of the triangle? Well, okay, well, know that BE does this here, right? We know that BE is congruent to itself. So in this situation here, it looks like I've got myself congruent triangles. That seems to work out. So therefore, we can say that triangle ABE is congruent to triangle CBE by side angle side, right? And as a result here, we know therefore that the pieces on the bottom, AE and EC, are congruent as well. So notice how there's this sort of matching thingy going on here. Because these initial segments match, these down here match, right? And so we can see that there's sort of a matching thing going on here. Now note that this works if AB is equal to BC, i.e. this is an isosceles triangle. If this isn't an isosceles triangle, however, things are going to change, right? Because if B can move over here, these are not going to be the same anymore, we can't use this argument. However, as it turns out that even though the triangles may themselves not be congruent anymore, there's still a relationship that goes on between them here. And that relationship is encapsulated in something that is known as the Angle Bisector Theorem, ladies and gentlemen. So, I'd like you to go ahead and take a look at this one here, folks. This is known as the Angle Bisector Theorem here. It says if a segment bisects an angle of a triangle, then it divides the opposite side into segments proportional to the other two sides. So, in essence, I'm attempting to prove AB over AE equals BC over EC here, or I can prove this. Either of these are perfectly fine. Both of these are valid things here. Now, this may seem kind of surprising to you, but this actually holds up pretty well. You can show that this, as long as you have an angle bisector up here, this works out very nicely. Okay, so this here is a, bit of a weird theorem. Like, where do we get this theorem from? How do we get this? So, this is what we're going to do. We're going to attempt to prove this theorem. I'm not going to show you why this works here. Okay, so I can try to show you how it works here. We'll take a look at what's happening. So here's our thing. It seems pretty fair. Now, whenever we see a proportion here, this reminds us, hey, wait a minute, this reminds us of similar triangles here, right? Because you've seen proportions with similar triangles. Okay, so I see these two triangles up here. I've got a pair of angles on top. So these two angles, ABE and CBE, certainly match. That's one pair of angles. It's wonderful. Now, unfortunately, ABC here happens to be just some rando commando triangle here. So, unfortunately, we don't have any information as to, to get another pair of angles. And that sucks. It's not really good here. So, we're going to have to do something a little bit different. So, bear with me, ladies and gentlemen, as we start this problem off here. Now, this proof here involves similar triangles. There is another proof out there that I may show you if I have time later on, but this works out very nicely. So, here's our original picture again, right? So, I have my original picture like this. So, here's AB and here's E here, okay? Here's my angle bisector, call this E. Now this is what I'm going to do. I'm going to create a new triangle here. Now, in general, I remember parallel lines generally mean congruent angles, so I like parallel lines. I'm going to create a line parallel to AB through C here. So I'm going to try to draw it parallel like so. There we are. So I want these to be parallel to one another, okay? So again, these are our goals here. I'm going to leave it on top. And I'm going to call this point down here X, okay? So I'm going to try to zoom out a little bit so you can see this a little bit better. All right, so, and then we're going to connect BE and extend it out so that we get X over here. Okay, so note here was we're going to create a line through C. Okay, so I'm just going to write this out here. I'm creating a line through C parallel to AB. And I want to extend BE to meet this line at X, okay? So notice that the red information here is what I've created to start. Alrighty, now, why parallel lines? Well, parallel lines are great because that gives us a lot of angles here, right? So we know, in particular, ladies and gentlemen, first off, we have now we have similar triangles. If we see these two triangles here, triangle ABE and triangle CXE, we suspect that they're similar, right? Can we show that these are similar? Well, I mean, there's enough information here, right? We have vertical angles here. So I can mark that like that here. So let me mark the two purple angles like so. I can say that angle AEB is congruent to angle CEX, right? These are vertical angles. Oh, that looks great, right? And then we also have the fact that we have parallel lines here, right? So therefore, I can say that angle ABE is congruent to angle CXE, right? These two angles are alternate interior angles, so I can mark that down here. So I can mark this here as well, so this marks with that. Okay, that seems good. So that means in this situation, these are alternate interior angles. And it's pretty clear by angle that these two triangles are similar. It's wonderful. Awesome. So we are in really good shape, ladies and gentlemen. I really like where this is going. So therefore, we know that okay, we have similar triangles. It's great, right? So now we can say that since corresponding sides, right? Now we know the corresponding sides of similar triangles are in proportion. We know that's the case here. Therefore, I can start writing a proportion. Let's see what matches. So I've got two. So notice how I can have both these sides AE and EC are opposite two purple angles here. So I can write that AE is going to be equal to EC. Or rather, AE and EC are going to be corresponding to one another, and therefore I can write a proportion, ratio. And note, this matches this up here. That's awesome. Okay. Now let's see. We notice that we have two vertical angles here, and these two vertical angles, the sides opposite them, are in proportion as well. AE matches with AB here, so I'm going to write that it's AB, and then this is going to be over, in this situation, this is going to be CX. So notice, ladies and gentlemen, we now have this is here, these are the corresponding sides, and therefore we're done. I wanted to say we were done, ladies and gentlemen. Unfortunately, we are not done. Because as you see here, this was our goal, and we kind of have almost our goal. We have this little thing here. God damn it, we have a CX. What are we going to do with that? Right? We'd like to get rid of it and replace it with BC. Well, maybe we can go back to our picture here. Let's take a look at our picture. We noted that ABE and CEXE were both congruent. They're both purple angles here. Wait a minute. If you think about it, everything we've done so far has been, pretty straightforward, but we never really used one important piece of information. The congruent angles on top. So this blue angle and this angle that's marked with a blue and a purple here, that matches this angle down here because it is also these are alternate interior angles. But wait a minute. ABE matches CXE, but wait a minute, ABE also matches CBE as well because this is angle bisector. So that means, in particular, all of these angles match. So that means I can write here something very important. We now have angle ABE is congruent to angle CXE, and it's also congruent to angle CBE. Wait a minute. I see something very sneaky here. We focus on this. CBE and CXE are congruent. This means that this triangle is what? Even though I didn't draw it well, this triangle is isosceles. And because it's an isosceles triangle, what do you know about isosceles triangles? We know that the sides opposite the congruent angles are congruent. Therefore, this matches that. And therefore, we can now substitute in. We have AB. We know CX matches BC, so I can swap that in and write it like this here. And we're done. And that's the proof. So this is a nice elementary proof involving similar triangles here. It'll work out very nicely.